Sup nerds. Today I want to talk about second order linear non-homogeneous ODEs with constant coefficients. And these are of the form ay double prime plus by prime plus cy equals g of t. So they're really similar to the homogeneous ones, except now instead of being equal to 0, it's equal to g of t. And so this left side we call the homogeneous part, and the solutions to these differential equations look like y of t equals c1y1 of t plus c2y2 of t plus y sub p of t. The c1y1 of t plus c2y2 of t is the solution to the homogeneous part. So they satisfy ay double prime plus by prime plus cy equals 0. The yp of t is called the particular solution. So the particular solution satisfies the original ODE. And we just need one single particular solution to make this entire right side a general solution to the ODE. So this is similar to if we wanted to solve the algebraic equation, 2x plus 4y equals 12. So there's infinitely many solutions because this is a set of points on a line. And so we have some solutions that look like 0, 3, or 6, 0, and a lot of stuff in between. And we could write all the solutions as t times 2 negative 1 plus some starting point 0, 3. Now this parameterizes all the different solutions for different values of t. So 0, 3 is when t is 0, and 6, 0 is when t is equal to 3. So this is one way of writing the general solutions. Another way would be if we had t times 2 negative 1 plus 6, 0. The second way also covers all the different types of solutions to the original equation. So just like these are two ways of writing all the solutions to this line, as long as we have one particular solution to the differential equation and then the general solution to the homogeneous part, then this gives us all the solutions. So the solutions to the homogeneous part are also called the complementary solutions, and I'll denote them as y sub h of t. So now let's look at an example. For this first example, let's take y double prime minus 5y prime plus 6y equals 30t. First we solve the homogeneous equation, and we get that the general solution to the homogeneous part is c1 e to the 3t plus c2 e to the 2t. Now we want to guess what our particular solution is. And it's a good idea to guess something that looks like our g of t, so it looks like 30t. So we want to take a general polynomial of degree 1, so at plus b. Now we want this b because when we take derivatives of the at, we're going to have lower order terms. So now we take this guess, take its first derivative and take its second derivative, and plug it back into the ODE, and then solve for what a and b have to be. So after we plug it back in and are careful with our algebra, we have two polynomials that are equal to each other. And so these two polynomials are equal if and only if the coefficients to each term are equal. So the coefficients for the t terms have to be equal, so we get 6at equals 30t, and then the constant terms coefficients have to be equal too. So negative 5a plus 6b has to be equal to 0. So we're left with two equations, two unknowns. We do a little bit of linear algebra, and this one's really simple. We just get a equals 5 and b equals 25/6. And so we get our general solution to this ODE is our homogeneous part plus our particular solution. So our particular solution is just 5t plus 25/6. As always, I suggest you pause and think about some of the steps within this solution. Maybe go back and watch it a little bit slowly if need be. You should make sure you understand why this is the solution and why we got a and b as they are. Now let's look at another example. So we have y double prime minus 5y prime plus 6y, which is the homogeneous part, and it's the same as last time, but the non-homogeneous part is going to be 4e to the t this time. So we have the same solution to the homogeneous part, and then this time we're going to guess our solution is going to be ae to the t, because we want it to look like 4e to the t, but maybe with a different coefficient. So just like the last example, we take the derivatives and then plug them back into the differential equation, and then we get an equation which allows us to solve for a. So we see immediately that a equals 2, and once you have a, you can plug it back into our particular solution and use that with the solution to the homogeneous part to get our general solution to the non-homogeneous ODE. Again, I suggest pausing and working through each of these steps a little bit slower if need be before moving on to the next one. Now let's look at one more example that's similar. So for this one, we have the same homogeneous part, but the non-homogeneous part is 20 cosine of t. So we're gonna have the same homogeneous solution. And this time our guess, we want y sub p of t to look like cosine. When you think about taking the derivative of cosine, you're gonna get sine terms. So let's make our guess y sub p of t a pretty general function. So a cosine of t plus b sine of t. And then once we take the derivatives, we're going to get more sine and cosine terms, this time with negatives, and the a's and b's are going to switch between being on the sine and cosine terms. And then, similar to the last two examples, once we plug it back in, we're going to have a big equation relating a's, b's, and other constants involved. And so if we have these two trig functions that are equal to each other, then it means all the coefficients for cosine have to be equal to each other. So combining those, we get an equation with a's and b's being equal to 20. And then similarly, all the coefficients for the sine terms have to be equal to each other. So we get an equation relating the a's and b's to 0 sine on the right-hand side. So we get two equations and two unknowns, which allow us to solve for a and b. And then once we have a and b, we just plug them back into our guess. And then our general solution to the ODE is the solution to the homogeneous part plus this particular solution. The next few examples are going to get a little bit more complicated, so make sure you understand these first three examples before moving on. Be sure to pause and rewind and work through some of the examples by yourself to get a better understanding. Now let's move on to the next example. So we're going to have the same homogeneous part for this one, but the non-homogeneous part is going to be 4e to the t plus 20 cosine of t. Now this might look familiar because this non-homogeneous part is the sum of the previous non-homogeneous parts. So we could go through this with the method of undetermined coefficients and guess a general formula. Differential equation. So the general solution to this differential equation has the same homogeneous part as the previous two, plus the sum of the last two's particular solutions. You may not be fully convinced that this is the solution, so I highly suggest pausing and working through a lot of the details of checking that this is indeed the solution to this non-homogeneous ODE. This idea is pretty powerful because it expands the different types of ODEs that we could solve. So now if our non-homogeneous part is an exponential, a sum of trig functions, or a polynomial, or some sum of them, then we can find the particular solution by splitting it up into smaller pieces and finding those particular solutions, and then just adding them up to get the particular solution for the sum of them. Before moving on to even more complicated examples, I wanted to do one with a different homogeneous part. So on this one, y double prime plus 9y equals some polynomial 3t squared minus t plus 1. Again, we could solve for the homogeneous part, which isn't too bad. And then we want to guess a general polynomial of degree 2, compute its derivatives, plug it back into the ODE, and then using the equations that we get from that, solve for what the polynomial has to be, and then put it back together to get the general solution. So I went through this one pretty quickly, but feel free to go through it a little bit slower if need be. This next example is going to be a little bit trickier. We're going to have y double prime plus 4y prime plus 4y equals te to the 3t. So this is a little trickier because the non-homogeneous part doesn't look like any of the ones we did before. Solving for the homogeneous solution is pretty straightforward again. But now for our guess, we want to guess something that looks like te to the 3t, but we won't just guess one term. We're going to guess a polynomial of degree 1 times e to the 3t. So at plus b times e to the 3t. And again, whenever there's a polynomial involved, you want to include lower order terms, because when you're taking the derivatives, you're going to have lower order terms involved. So again, we compute the derivatives, we plug the derivatives and the original guess back into the ODE, and then all the terms are going to have an e to the 3t in them. So we could divide that out, and then just solve for a and b. And then once we have a and b, it's similar to the previous ones where our general solution is the homogeneous solution plus the particular solution. Let's look at a similar example with the same homogeneous part, but this time the non-homogeneous part is t cosine of t. So we have the same homogeneous solution. Our guess should be a general degree 1 polynomial times cosine, and we also want a sine term in there, so a general degree 1 polynomial times sine. So we have 4 constants. Again, we take the derivatives and we plug them back into the differential equation. There will be a lot of terms after plugging it back into the differential equation, so it's still important to organize them by what term each of the constants are attached to. So gathering all the t sine of t terms, the t cosine of t terms, the sine of t terms, and the cosine of t terms, we're going to have 4 equations with 4 unknowns, and we'll be able to solve for all 4 constants. So this part is just linear algebra. Besides being careful with all of the algebra, the tricky part of these problems is guessing the correct form of the solution. That way you could solve for the correct constants. Before moving on to the last 2 examples, be sure to pause and work through some of the details of these problems. The best way to get the hang of them is by trying a few examples on your own. So now let's move on to our second to last example. We're going to have the homogeneous part be something we saw before, so we're going to have the same homogeneous solution as before. But now for our guess, we need to be careful because our normal guess would just be ae to the 2t, but that's already one of the solutions of the homogeneous part. So what we want to do, and we saw this before when we were doing repeated roots in the last video, we want to take this guess and multiply it by t. So once we multiply it by t and then take the derivatives and plug it in, when we plug it in, we could ignore all the e to the 2t's because all the terms are going to have that. And after plugging it into a differential equation, we'll be able to solve for a. And you could check that this is indeed a solution to this ODE. So the idea is if your particular solution looks like one of the homogeneous solutions, you want to multiply it by t until all the terms of your guess are linearly independent from the homogeneous solution. Examples like this where the non-homogeneous part looks like the solution to the homogeneous part usually give people the most trouble, so pause and think about why this particular solution works and how it's similar to how we solved the homogeneous equation when we had repeated roots. Let's move on to our last example, and this one's going to be extra tricky. So we're going to have a homogeneous part that we had before, and this time our non-homogeneous part looks like the homogeneous solutions. So if we had a different homogeneous part that didn't look like this non-homogeneous part, we would just guess at plus b times e to the negative 2t. But this looks like our homogeneous solution, so let's take a look at what happens if we just multiply by t. If you just multiply by t and then take the derivatives, we don't even have to consider the bt e to the negative 2t because that would get absorbed into the homogeneous solution. Now, I suggest you work it out with the b's involved, but when you're doing your linear algebra, you'll get that b is a free variable. And then when you're trying to solve for a, you're going to get 2 different values for a, which is inconsistent. So that means the particular solution can't look like this. So this is an instance that I was talking about before, where we need all of the parts of our particular solution to be linearly independent from the homogeneous solution. So we can't just multiply by t, we need to multiply by t squared. And after you do that and take the derivatives and plug it in, you'll be able to solve for what the particular solution looks like. So I worked through the details here where we multiply by t squared. Most of it's just tedious work, but it's not too difficult once you have the correct guess. So again, it might help to go through a little bit slowly, work through the details yourselves. Hope you enjoyed this video. If you smash that like button, subscribe, and drop any comments or questions below. And until next time.